Hello, welcome to my channel. Welcome to Rehandran. Today I'm gonna talk about electromagnetic fields, essentials of electromagnetic fields, the prerequisites. So to go into the topic of EMF, first you gotta know some basic concepts and rules and laws. Okay, and so in this first introductory video I'm going to talk about coordinate systems, especially orthogonal coordinate systems. Okay, so uh, in this video of EMF 101 I'm going to talk about orthogonal systems. So electromagnetic fields are not only function of time but also space. Okay, so the physical quantities regarding EMF are both functions of time and space. So we write EMF is both function of time and space, and electromagnetic fields are vector fields. Okay, so electromagnetic fields are vector fields. EMF is a vector field. So the fields in electrons as a whole is a vector field, and there are two distinct but related fields in an electromagnetic field as a whole, which is electric field and magnetic field. These two fields are vectors individually also, and together they form electromagnetic field. If this is the electric field and this is magnetic field, this is E and this is B, and this is the direction of X and Z, say. So E is in the direction of Z, B is in the direction Y, then the resulting waveform is in the direction of X. So the uh, uh, the resulting waveform goes in the direction of X at velocity u, say, at velocity u. Okay, so to describe EM field we have to be able to describe its orientation in a coordinate system. So in that case we need to know about, for that case, okay, so to describe the orientation and calculate EM field as a whole, we need to understand how to describe and represent electromagnetic fields in a three-dimensional system. That's why we need to understand what orthogonal systems are. Orthogonal coordinate systems are systems in which the coordinates are mutually perpendicular to each other. Okay, so as EMFs are vector field, so to describe a vector accurately and express a vector in terms of its components, so a vector has uh, three perpendicular components in the three dimensions. um, we need to refer these components in certain directions, which we say reference directions. Like uh, almost all of us know about Cartesian coordinate system. Okay, we use it basically in every mathematical and physics problems and graphs, etc., to describe an object. Orthogonal coordinate systems are of most um, useful, and they are practical. The non-orthogonal systems are not that practical. So the orthogonal systems are easy to use, manipulate in case of electromagnetic fields, and they are practical. So coordinate systems which are mutually perpendicular to each other are orthogonal systems, like Cartesian coordinate system, where the coordinates or axes are perpendicular to each other. All of them are 90 degree, 90, 90. So like Cartesian system, there are two other which are cylindrical and spherical systems, coordinate systems. Now we will discuss about them. Okay, these are the three orthogonal coordinate system in which the coordinate variables and the coordinate axes are perpendicular to each other. That's why they're called orthogonal systems. And the variables for Cartesian system is are x, y, z, for cylindrical rho, phi, z, and for spherical r, theta, rho. The coordinate variables are x, y, z, uh, for cylindrical rho, phi, z, and for spherical r, theta, phi. These are the coordinate variables. Now we are gonna discuss about their ranges. So the range of xyz variables are minus infinity to plus infinity. All the three have the ranges from minus infinity to plus infinity. Z infinity. For cylindrical system, the coordinate variables have the range. Rho is the length from 0 to infinity. So length of the cylinder, you can say radius. So infinity. Phi can only, phi is an angle, it can only travel angular distance from 0 to a full circle of, or 2 pi radian. 0 to phi to 2 pi, and z is the same as the z of Cartesian, so minus infinity z to infinity. For spherical coordinate system, the variables have the range. R is 0, R is from 0 to infinity. Theta is also angle, which is from 0 to half circle. It can cover distance half circle, so 0 to pi radian. So 0 to theta pi radians, and phi is the same as phi of cylindrical system. 0 pi to pi radian. Okay, these are the ranges. Now we are gonna discuss about the relationship among the three variables of the coordinate system, among the variables of the three orthogonal coordinate systems. So as for the relationship, in terms of, say, we want to let me first draw some diagram. You see, if you say this is x and this is y, so if you now see that from this diagram, this graph, that rho is completely on xy plane, and rho does the angle phi with x axis. Okay, and uh, here if we see, r has, this is rho, r is totally on the z and rho surface. So if we draw this is rho, this is Z, this is R, this is theta. Okay, this is for now for relationship we can say we want to express y in terms of rho, so x will be rho cos phi, y in terms of rho is rho sin phi, as we can see. Now in cylindrical system, rho can be represented in terms of r. So how can we represent r? um, rho in terms of r, so rho in terms of r can be represented by r sine theta, and z can be represented by r cos theta, and phi here phi can be represented in terms of y and x, tan inverse y by x. Now rho, if rho is r sin theta, so we can replace rho by r sin theta and get x in terms of r, so equals to r sin theta cos phi, and y is r sin theta sin phi, and in term rho r is this x square plus y square plus z square, and here rho can also be written as over x square plus y square, and um, theta can be represented by tan inverse, what, tan inverse rho by z, or we can also write cos inverse z by r. So these are the basic relationships among the variables. Say a is a vector, this is the a vector a with its components a, say this is a with its all its components. Okay, how are you gonna how are we gonna represent a in Cartesian? In a vector a in Cartesian is defined as its x component in the direction of x with unit vector ax plus a y component in the direction of y with unity vector ay, and az with component vector az, and in the direction of z with unit vector az, and its magnitude is obviously is ax square plus ay square plus az square. In cylindrical system, vector a is represented as a rho in direction of rho, unit vector a rho a phi, unit vector a phi plus a z component in direction of z with unit vector a z, and its magnitude is a rho square plus a phi square plus a z square. A in terms of spherical vector a in terms of spherical coordinate system can be represented by ar in direction of r with unit vector ar plus a theta component with unit vector a theta plus a phi unit vector a phi, and its magnitude is a r square plus a theta square plus a phi square. Now we are going to transform the from one coordinate system to the other and vice versa. So first we have to define the vector unit vectors. Okay, unit vectors from one to other, from say from cylindrical, from Cartesian to cylindrical. So uh, say for Cartesian unit vectors ax, ay, az corresponding a row, what will a row be? Okay, so if we see this diagram, we will be able to see that row has component cos phi in the direction of x. So in the a row has a x component, unit vector ax component cos phi f ax. So now for in the y direction it has sine component sine phi ay, plus it doesn't have any component on the z axis because rho and z are perpendicular to each other, so 0 az. Now for a phi, to uh, know about a phi we have to draw another diagram. Okay, so let me draw another diagram, this. So if this is in the direction a row, so for phi, this is phi obviously, so phi is in the this direction. Okay, this direction. So let me draw like this, a phi, this is y. So a phi, if this is phi, a row has the has phi angle with y, this is minus direction, so ax, this is minus x. Okay, so we can see that a row has minus sine phi component in the direction of x, so minus sine phi ax and plus cos phi because it has cos angle with y, ay cos phi ay. All the unit vectors are in the direction parallel to the direction of the axis. So ay is in the direction of y, ax is in the direction of x, a row is in the direction of a row, a phi is in the direction of the angle is tangential to the angle, this. So a row. Okay, and a row doesn't have any component in the direction of z because a row and az are perpendicular to each other, so it has no component, zero component. So plus 0 az, and az is basically az, it's the same as the z of Cartesian system. So these are the unit vectors in cylindrical from Cartesian. Okay, now if we want to do the vice versa, so from cylindrical to Cartesian, so ax has the component phi cos phi, so cos phi a row, and y has sine phi and a phi uh, with a phi, ax has minus sine phi component, so minus sine phi a phi plus 0 az. Okay, ax is perpendicular to the z direction, az unit vector. Now for ay has sine phi component to a row, sine phi a row, and with a phi it has plus cos phi component phi a phi plus 0 az. Okay, and Az is the same as z of cylindrical. These are the relation between Cartesian and cylindrical systems in terms of vector. If we want to convert a vector a representation in Cartesian system to cylindrical, it will be this. And if we want to convert cylindrical to Cartesian, it will be the unit vectors will be like this. And we in later we will represent the full vector in terms of xyz with the corresponding components in the respective coordinate systems. Now we want to uh, transform cylindrical to spherical or spherical to cylindrical. How are we gonna do that? Okay, so AR has the component sine theta in the direction of rho, so a rho, so plus sine theta a rho. And for phi, if we see, phi has the direction in this direction, phi goes, this is phi. So if we write like this, so phi is in this direction, it's we can see that r is perpendicular to phi, so it has no component in phi direction, 0 a phi. We can see that it is 90 degree, okay, in the phi direction, phi in this direction. Okay, now for z, in terms of z, we see that from this z has cos theta component, so cos theta in the direction of z, so unit vector is z. For a theta, you can see that if we want to say here, so this is rho, this is r, and theta is in this direction, so this is a theta. Okay, so this is z and this is minus z. Okay, and if this is theta, uh, we can say theta is this also, huh? If you ponder this, it will be like this. So the direction of a theta, so a theta has plus cos theta component in the direction of rho, the direction of rho, so cos, as theta is an angle, the unit vector will be tangential to the tangent to the um, tangent. This is this a theta is the tangent of the angle, arc or arc, what you may say. So cos theta a rho, and phi theta is perpendicular to phi, so no component, so plus 0 a phi, so this is plus, and with az it has minus sine theta, so minus sine theta in the direction of z with unit vector az. So this is the a theta in terms of rho phi z. Now a phi is the same as phi a phi in the cylindrical. Now if we convert spherical a vector in spherical to a vector in cylindrical, how would it like? So the unit vector a rho in terms of rho phi, rho theta phi, r theta phi is, so from here we can say a rho has sine theta component, so sine theta in the direction of r, so a r. Now for theta, rho, a rho has cos theta component in the direction of a theta, so plus uh, it is plus cos theta a theta, and rho is perpendicular to z, so no z component, plus 0 az. So now a phi is the same as a phi in the spherical system. And for az, okay, az has cos theta component in the direction r, so ar plus minus sine theta in the direction of a theta minus sine theta a theta, and perpendicular to phi, so plus 0 a phi. So these are the transformation from cylindrical to spherical or spherical to cylindrical for a vector. Now what will be the transformation of Cartesian to spherical and vice versa? We will now see that. If we see in this in this diagram, r has sine theta component with rho, and rho has cos phi component with x. So ar has sine theta cos phi component with ax in the x direction, okay, plus r has sine theta component and rho has sine phi component. So ar has sine theta sine phi component with unit vector ay in the direction of y. So sine, this is sine, okay, sine theta sine phi in the with ay in the direction of y. Ar has in the component cos theta with az, so plus cos theta az. Now theta a theta has cos theta component with rho, and rho has cos phi component with ax, so a theta has cos theta cos phi component with ax plus obviously cos theta again with ay, obviously cos theta sine phi component with ay plus now it will be minus sine theta component with az, okay, so minus sine theta component with az. Now phi in terms of xyz will have, from this diagram we can see that phi has minus sine phi component with ax and plus cos phi with ay, plus cos phi ay and 0 component in the direction, because phi is perpendicular to az, so no component. So for spherical to Cartesian conversion, ax will look like, so ax has component, x has cos phi with a rho has sine theta component, so ax has cos phi sine theta with ar component. Now ax has cos phi with rho, and a rho has sine theta component, so ax has let me write in this cos phi cos theta a theta, and az is a phi, and ax has minus sine theta sine phi minus, so and ax has minus sine phi, so minus sine phi component in the direction phi a phi rho r theta phi. Now for ay has sine phi component with arrow, sine phi arrow has sine theta component ar. So sine phi sine theta ar plus or minus ay has sine theta sine phi component plus sine phi. Arrow has cos theta component, so cos theta a what a theta with a theta. Let me write it cleanly. So y has sine phi component with rho sine phi, and rho has cos phi component here, cos theta component, so cos theta component with a theta, so in the direction of a theta, okay. And phi, for phi y has cos phi component with a phi plus cos phi a phi. For az now the last transformation, so az has here az has cos theta component, cos theta with ar in the direction of r, so cos theta ar minus sine theta a theta, so minus sine theta a theta, and is perpendicular to phi, so 0 component with a phi. So this is the last transformation from rectangular to spherical and spherical to Cartesian or rectangular. So that's it for today. I hope you understood the relationship among the three orthogonal coordinate systems and their transformation. And in the next video I am doing some numericals, and then immediately after that I will go to vector calculus, and then we will go to the main EMF chapter. Okay, thank you for watching, and if you have any problem in understanding my explanation, you can write in the comment section, and please do subscribe. I'm trying to upload as many videos as possible, and I want to um, uh, explain and discuss about EMF, circuit theory, and almost everything in electrical mechanical engineering. So support me and subscribe to my channel, and if you have any problems, send me. We can discuss in future, and thank you.